Hi, I'm Jana Levin. I'm a professor of physics and astronomy at Barnard College of Columbia University. And today I've been asked to explain black holes in 5 levels of increasing complexity. A black hole might be different than you imagine. To some extent, it's a place and not a thing. Black holes play an important role in the history of the universe, in sculpting galaxies that we live in, and possibly in the ultimate fate of the universe.
Hi.
Hi, welcome. Tell me your name.
Jude.
I wanted to ask you if you have ever heard of a black hole.
Yeah, I think that they're scary and cool because you can get sucked in and get lost forever and get plopped out in a random place. It's like a big, giant, black thingy.
So black holes, you describe them as huge. The interesting thing about black holes is they're hugely heavy, but they're actually physically really small. What really matters is the density. Do you know what density is?
It's not weight, but it's how much of it is in it.
Here, let me show you something. I can ask how heavy it is.
Yeah.
I can also ask how big it is, which is a question about its volume. If I make it smaller, then what's happening is it's becoming more dense. So imagine I crushed this really, really small. It would weigh the same. It would have the same mass, but it would be much more dense.
How does it go that small?
If a star is heavy enough to explode into supernova, what's left begins to collapse under its own weight. And if that's heavy enough, the core will not be able to stop collapsing because it no longer has the thermonuclear fuel. It's run out of fuel. And if it's run out of fuel, it's no longer shining and pushing outward. And without that, it itself begins to go dark and there's nothing fighting the collapse anymore. And that's when you form a black hole.
So if like the sun all collapsed on itself, it would form a black hole?
Well, that's a really good question. So interestingly, the sun itself isn't heavy enough. So it has to be heavy enough that when it begins to collapse, it just overcomes all attempts to fight it. If you made something really dense, you would have to travel faster than the speed of light to actually escape. That's 300,000 kilometers per second.
Oh, it goes so fast that it's all dark?
So it goes so fast that it goes completely dark. Any light that veers too close will fall in, will not be able to make it back out again. If a light is shining from the sun near a black hole, the black hole's not touching it. Why does the light get pulled in? Why does that happen?
Because the black hole is taking other stuff?
It is taking other stuff, but the funny question was like, if I wanted to move your chair, you'd think it was really strange if I didn't have to come near you and actually grab the chair and move it. One of the things Einstein thought about is he imagined that what the black hole is doing is it's changing the shape of space around it. What do you think of that idea?
That's crazy.
Isn't it crazy? And then Einstein goes a step further and thinks, well, what black holes must be doing is curving the space so strongly that even light gets caught. Sometimes you can get light caught into a whole orbit. Literally the light going round and round in an orbit.
So a black hole, it doesn't attract light. It moves the space so that the curve is pointed towards it?
That's right. We've been talking for a little while about black holes. What are you going to walk away with in your impression of what a black hole is?
It's kind of curves in space that are all coming to one point. Everything that goes on those curves changes directions to come in. And even light can't escape it. Nothing can.
You said that very beautifully. Does that feel like a different idea of a black hole than the one you had before we spoke?
Yeah, a lot.
Have you heard about black holes?
Yes. I know it has a lot of mass, but it's very small. I know that there are several theories about the universe due to black holes, like around the universe and how it's made.
So a lot of times stars are born together in 2 star systems. And when they die, if they're heavy enough, they will collapse under their own weight and form a black hole. So here you have a black hole and a big fluffy star. And what will happen is it'll start to tear apart its neighboring star. Literally parts of the star will begin to spill onto the black hole and splatter on the black hole. But let's say both those stars formed black holes. And what these black holes do is they are like mallets on a drum. They create literally waves in the shape of space-time as they're moving. So imagine mallets on a drum, how the drum ripples. Depending on how the mallets are moving, you hear different sounds. So effectively, these black holes, as they get very close together in the final stages of their life together, they're orbiting each other at hundreds of times a second. It's this really crazy event, but it's happening in complete darkness. Eventually, they bobble together and they merge, and then they ring out. The space-time's going crazy around them. It's the storm in space-time, and they settle down to a quiet black hole. Then those waves that they created travel through the universe basically undisturbed. For a long time, people thought, well, even if black holes are out there, they're impossible to observe.
Yeah.
And then they got very clever. You might wonder how we could possibly hear black holes. That sounds crazy. So I'm going to show you, but I'm going to need your help. This demo involves an electric guitar. Do you play it all?
A little bit.
Okay, you want to do the demo for me? So the LIGO instrument electronically records the ringing of the shape of space with its very complicated instrument. It stands for Laser Interferometric Gravitational Wave Observatory. And the design was incredibly difficult, and they didn't know if they would succeed. I think of the instrument as like the body of the electric guitar. And then they take the readout of the motions of the waves that they're recording, just like that guitar is recording the motions of the waves on the string. I just play it like a little bit. And you can't hear anything, right? You're not meant to hear an electric guitar when it's not plugged in. What's happening is the guitar strings are ringing, but so quietly that we can't actually hear the sound. And this is like the gravitational waves, which are ringing the drum of space-time, but so quietly that they're not moving the air and we're not hearing them. So now play, and I'm going to turn the volume up a little bit. While I can't actually hear the ringing of the strings themselves, I can hear the data of the shape of the string recorded and played through this amplifier. And that's kind of the idea behind the LIGO instrument.
How do you know that it's like the black hole that's making that sound and nothing else?
It's a great question. If I didn't see you playing the guitar, I would recognize the sound of a guitar. And even if I'd never heard of a guitar before, I could figure out the frequencies that the string was playing. I could tell how strongly it had been plucked, and I could tell the length of it and where it was pinned down from the harmonics of the string. And I can tell the different lengths of the strings from the notes that they play. So I can actually reconstruct the instrument that's playing it. And it's very similar to LIGO. We can listen to the notes, the amplitude, the harmonics, and we can deduce the size and shape of the objects doing that. And they're very massive and they're very small and they have all the markings of a black hole.
Is there anything that like gets affected on Earth because of those waves?
It's a really good question. Only this instrument. And that's why it was so hard to build. And by the time it gets here, it's so weak that it's only squeezing and stretching space at like the fraction of a nucleus over very large distances. Has your understanding of black holes changed over the course of our conversation?
I knew there were waves for like everything, but I never thought specifically, oh yeah, black holes have like waves. I know more and less.
I know what you mean.
I'm Jada. It's nice to meet you.
Nice to meet you. And where are you studying?
I'm a senior at NYU. I'm studying physics and environmental studies.
What is your impression of what a black hole is?
So it's a star that has collapsed. It has so much concentrated mass and gravity that there's a point outside of the black hole called the event horizon. So once you get past the event horizon, nothing, not even light, can escape from that.
So that's a great definition, and I want to pick that apart a little bit. So what you described is just right. Stars, when they run out of thermonuclear fuel, are going to collapse under their own weight. It'll explode in a supernova, it'll leave a core, and if the core itself is heavy enough, it will keep collapsing. It does, as you say, reach this point where not even light can escape. But the amazing thing is it leaves that point, you called it rightly the event horizon, it leaves it behind kind of like an archaeological record. Because the star itself can no more sit at the event horizon than it can race outward at the speed of light. So the core of the star keeps collapsing. And where it goes, nobody knows. So in a weird way, the black hole isn't anymore a crush of matter. It left it behind in its wake, but the stuff of the star is gone.
I've heard of Schwarzschild black holes, which is a black hole that is static, a Kerr black hole or a Kerr-Newman black hole, which is a black hole that rotates. But what makes a black hole static versus rotating, and what's more common?
It turns out that there are only 3 quantities that define a black hole. It's electric charge, its mass, and its spin. So the most general black hole can also spin, and it can also be electrically charged. Whether or not they are has to do with how they formed. If a star collapses, it will likely be spinning when it collapses, and the remnant black hole that forms will likely be spinning. A black hole of a certain mass, charge, and spin is indistinguishable from any other black hole with those same properties. So in some sense, they're like fundamental particles, which makes them absolutely exceptional for any other astrophysical object. Have you heard the stories about what happens inside a black hole?
I remember that once you pass the event horizon, space becomes time and time becomes space in like a coordinate sense.
So from the outside, if you're an astronaut, you're watching your friend, another astronaut, who going into the black hole, it's as though your times become rotated relative to each other. So the profound thing is, as an astronaut on the outside, looking at this round event horizon, you think of the center of black hole as a point in space. But to the person who's fallen in, it's not a point in space at all. It's a point in time. The singularity, or the end of it all, the crush in the center of the black hole, is in their future. So they can no more avoid the singularity than you can avoid the next instant of time coming. So the death in the singularity is inevitable, although we don't really think the singularity necessarily exists.
I sort of know what a singularity is. I think of it as something where everything is compacted into one single point. It's a place where the laws of physics don't exactly work out. What did you mean when you said that you don't think the singularity really exists?
So the singularity is definitely predicted in Einstein's general theory of relativity, and that's purely a theory of space-time. And in the theory of space-time, there is no question that a singularity would form when the star collapses catastrophically inside the black hole. Now, even when people talked about singularities back in the 60s, they thought, quantum mechanics is part of the story of the whole of physics. It's not just gravity. And if we understand quantum gravity, we'll realize that singularity probably doesn't ever actually form.
So since we obviously have never been to a black hole, how do we know for sure, what happens after you cross the event horizon, or what happens inside a black hole? Is it just inferred from the math?
I would say to some extent we don't know for sure. What we have found is that the mathematics is so unbelievably powerful that we're able to disprove wrong ideas just in pen and paper. Just very recently, within the past couple of years, the first ever human-procured image of a black hole showed us what we expected to see of the event horizon. So Jada, after our conversation today, what would you say a black hole is?
Something that I had never thought of before is a black hole as kind of a type of quantum fundamental particle. I've also learned how the event horizon of a black hole kind of hides a singularity.
The beauty of being a student of something like black holes is you never stop having new impressions of what this enigmatic phenomena is. So in a year, I'll tell you what I learned that's new.
Awesome.
I'm Claire.
And you're in graduate school, and you're getting your PhD. What year are you?
I'm a second year. So I'm measuring star formation histories in the small and large Magellanic Clouds.
Does the Large Magellanic Cloud have a big black hole?
So I think the prevailing wisdom for a while was no, but my answer, honestly, is I'm not sure.
Yeah, and probably nobody is. Have you heard a lot in your studies about these supermassive black holes that we think lurk in the centers of very nearly every galaxy?
So I don't study AGN a lot, but I do have a long-term interest in black holes. It's one of the reasons I entered the field. I always was curious about how a black hole of that size was able to form. Was it the result of mergers between smaller black holes, ultimately creating a gravitational well deep enough to contract a protogenic disk for a whole galaxy? Or, man, what happened?
Yeah, I think it's a really good question. The only mechanism that we know for sure can form black holes is the collapse of very massive stars. So it's sensible to think, well, maybe some very massive stars in a young universe collapsed under their own weight, and then they merged, and after some time they got big enough. But the black holes from stars can be tens of times the mass of the sun, maybe hundreds of times the mass of the sun if they merge. To get to millions and billions, and if you just do the simple arithmetic of how many years that would take, there aren't enough years in the 14 billion years of the universe's lifetime. So they must have come from somewhere else.
I am at a loss to think of what could have possibly happened in between the start of the universe and the formation of our galaxy that could create such a massive object.
Yeah, I think that's right. I think people are really perplexed about how you make something so big in such a short period of time. It's kind of funny, the bigger you make a black hole, it seems maybe counterintuitive, but the less dense the material has to be out of which you make it. So you can, out of something the density almost of air, you can make a supermassive black hole. You can't make a star out of that. But weirdly, if you skip the star phase altogether, it's conceivable that they directly collapse. And so there's suddenly a new way to make black holes that nature has figured out.
We spend all of our time, when we learn about black holes in school, predominantly through star collapse.
Yeah.
I didn't even realize that there was an alternate route to creating a black hole.
There might be many alternate routes. It might be in the very early universe that bubbles in unusual phase transitions from very high energy universe to a low energy universe can make black holes. We haven't really thought of the range of possibilities. And so there could also be primordial black holes that are still around that also skipped the star stage altogether, that were formed really in the very earliest phases. And I think the interesting thing is, with you looking at like the Large Magellanic Cloud, is to wonder if we're going to merge.
Absolutely. We thought the canonical picture of the clouds was essentially that they had formed with the Milky Way, maybe in its halo, and had been in a stable orbit for about a Hubble time, or about 14 billion years. Young guns in the field have thrown a wrench in that theory that they've always been orbiting and that perhaps they're on their first orbit. They're on an unstable orbit. Will they join us?
Can you tell us about Andromeda?
Andromeda is part of the big three in the local group.
The local group being a group of galaxies that are not expanding with the expansion of the universe away from each other. They're trapped.
Gravitationally, all friends.
Yes, they're all friends.
And Andromeda is one of the few galaxies that is traveling towards us, and we are due for a merger event at some point. So given a sufficiently low velocity, we would just have two big galaxies that, for the most part, pass through each other, pass by each other. But given a sufficiently high velocity, we will have some crazy black hole interactions and some crazy star interactions.
But when we do merge with Andromeda, presumably our black holes will merge, and Andromeda indeed has a very big black hole as well at its center. And then we'll have this just gigantic...
Super massive black hole.
Yeah, and it's very possible that, as you said, the collision won't be so severe that it'll be very disruptive, so our entire solar system could stay intact. And here we would go with the sun and all the other planets in orbit around a new black hole.
They're kind of misunderstood giants in a way. So I was curious, have you heard anything new or interesting in the field of black holes that will shape future discussions?
We work a lot right now on thinking of black holes as batteries. So a black hole that can take like a giant magnet, astronomical magnet in the form of another collapsed star like a neutron star, and flip it around so fast near the speed of light that it actually creates an electronic circuit out of this moving magnet. And so that the power that can come out of these electronic circuits created by these batteries can be tremendous.
You know, I know that at a certain point, for our civilization to become sufficiently advanced to travel the cosmos beyond, the moon or Mars, we may have to be able to harness the power of our sun. Would it be similarly possible to harness the power of a black hole, like you were mentioning, to travel?
It's a great question. I once did a calculation of using a black hole made out of the moon and the strongest magnet we could find on Earth to see if I could make an electronic battery. And honestly, you only get about enough energy to power New York City. But we have to find one in our neighborhood first.
Yeah, wouldn't be my favorite thing.
So Claire, we've had this pretty fascinating conversation about supermassive black holes in particular. And after our discussion, what is it that has changed for you in your perspective, or what is it that excites you?
So I think our discussion kind of exposed a piece of black holes that I don't think of often, which is that they're not just life takers, they're life givers. And they inform a lot about not just how a galaxy is destroyed or made, but how it's shaped and how it eventually, builds life like ours. So maybe I have to give black holes a little bit more props.
Hi, Dan. I'm so glad you could make it. What have you been working on with black holes in the time since I've last seen you?
There are a lot of aspects to black holes. The one that's kind of interested me most lately is trying to understand them from the point of view of information, how information is stored and processed and recovered from black holes, which turns out to be a really interesting perspective.
Talk us through Hawking's initial revolution that led to a lot of these conversations about the information around black holes.
Hawking's big insight was that he had to apply both the rules of quantum mechanics and the rules of gravity to really understand how black holes behaved. But Hawking took a point of view where he brought quantum mechanics into the game. He realized that if you took that into account, that it's actually not quite true that black holes are black, that actually things can escape from black holes.
So what you're describing is the famous Hawking radiation, where a black hole cleverly kind of steals energy from the quantum vacuum and radiates, and in the process evaporates. And of course, this caused a big kerfuffle, because when the black hole evaporates, eventually that event horizon is yanked up, and the question is where did everything go that had once fallen in?
A way to think about Hawking radiation is to imagine that pairs of particles and antiparticles appear out of the quantum vacuum, and the particle can escape the black hole, but the antiparticle falls in. But the particle and antiparticle are a pair. And if the antiparticle really falls into the black hole and is destroyed at the singularity, that poor particle outside the black hole has lost his partner. It also violates the rules of quantum mechanics. If you have two particles that are entangled, that has to be preserved.
Now, to be clear, nobody disputes that black holes will quantum radiate, that Hawking radiation is a solid prediction. The black holes should, in fact, evaporate. That's not disputed, right?
That's right. It would be wonderful if we could have some experimental evidence for this, if we could really build a black hole in the lab and test to see whether it behaves this way. But I think there is hope that we'll be able to detect some of these effects either indirectly by looking at black holes out in the universe, or also maybe indirectly in the laboratory by looking at systems which aren't black holes, but which radiate in kind of similar ways.
There's this domain of black holes in astrophysics, where we see stars collapse and we know that they exist, and there's whole observational astronomy around them. And then there's this domain that we're talking about, where, as you said, black holes are so special because they're kind of guiding us in the right direction to understand the very nature of reality. And that makes them really unusually special. And one of the things I wanted to draw out is that we talk about the fundamental forces of nature. So there's the matter forces, and then the outlier is gravity. We've quantized all the matter forces in a way that we're rather comfortable with. Gravity keeps resisting quantization of gravity itself. And now we're thinking in a way that you're describing that, well, maybe it's only the quantum forces altogether.
The pursuit of quantum gravity has taken us to places we never expected to be. I think what's exciting about physics, about theoretical physics, that you start following a thread, you start developing a chain of logic, and you never know where it's going to end up.
Do you think there's ever a hope that the kind of information that you think about, the quantum gravity aspects of the universe that you think about, whether it will pan out or not, will ever be viably observed in these astronomical pursuits of the event horizon?
It's a real challenge, but astronomical observations have gotten so fantastically precise. And there is some hope that if you looked at things like two black holes merging, each black hole comes in with its own event horizon. But then when the black holes merge, there's a very complicated process where these two event horizons merge and oscillate and vibrate and then settle down into a single event horizon for the final black hole. There is some hope that if we can make sufficiently detailed observations of this process, if we could really see the way the event horizon is behaving as it settles down to this final state, that maybe that could reveal some of these quantum effects that we've been talking about.
It is amazing in the numerical simulations of two black holes merging, you really see the event horizons bubble around. And we were talking earlier about how really black holes are flawless. They don't tolerate those kinds of imperfections. And so you can so quickly watch the system wring away that misshapen merger, and it comes out in the gravitational waves, which is literally the ripples in the shape of space-time, until it settles down, and then it's utterly flawless again. It really happens fast. It's quite amazing.
Yeah, it's a spectacular process.
In some sense, black holes aren't anything anymore. They're just empty, curved space-times, and nothing is there. How would you possibly make one? And then it becomes, why are there so many? And where are they all? Being a black hole scientist means each question leads to more questions. We know more and more, but we also see how much more there is to understand. I hope you've learned something about black holes. Thank you so much for watching.